Hello, hope everyone's well. So again, we're at a point now where we are reaping the benefits from the hard work that we went through in chapter 3 and 4. So we have some idea of what confidence intervals and hypothesis tests are about, and it's just a question of dropping them into different circumstances. So we drop them into the circumstance of where we're studying one proportion. We drop them into the circumstance where we're studying one mean. Last video was the circumstance where we're studying two proportions, a percentage of men, percentage of women, for example, and today we're talking about two means. So two means might be, for example, you have an average for people who are taking the blood pressure medicine and an average for people who are not taking the blood pressure medicine. You might have an average for people who go through the French educational system and an average for people who go through the Polish educational system. So you have two means, and the question is going to be, if we find some difference between the two, is it just because it's a sample thing, or is there a genuine difference between the two? That is to say, what is the difference in the population given that we have samples? So we have a sample of, let's say for example, we have a sample of treatment group and control group, and we're looking to know whether where would the census average and the census average for what would be the difference between the two census averages if we didn't give this medicine to only 23 people, we gave this medicine to 203,000 people, kind of stuff. What would be the true difference in the means? So as always with confidence intervals and hypothesis tests, we're trying to express that we have a sample and we want to know about what would happen if we took a census. Okay, the formulas, as with the previous sections, the formulas are just formulas and just a question of dropping into them. And there's always some little twist, but every one of these has a little twist, but it's not especially hard. The hard part is the idea. What's a confidence interval about? It's not about the sample, it's about the population. What's a hypothesis test about? It's again not about the samples, it's about the population. So we have two means, mu1 and mu2. For example, just to take an example, we might give fourth graders a math test, and we're interested in how fourth grade boys do compared to fourth grade girls, just as an example. Is there a difference, yes or no? So, So we have two contexts. This context is where you know the standard deviation of the underlying population, and I'm going to focus today on the much more common case where you don't know the standard deviation of the underlying population. You have an x1 bar and an x2 bar, but the context here is that you know the standard deviation of the underlying population for those two. But I'm going to focus on this context here, where we don't know the standard deviation of the underlying population. And we saw this already in the one mean case when we were looking at we had an x bar, we're trying to figure out about mu, but we also don't know sigma. So we learned in that chapter, section 6.2, we learned that in the context of means, you have to go and look things up on a slightly different curve, because in this context, there are two things you don't know. You not only don't know the mean, but you also don't know the standard deviation, and so you're sort of twice as confused, and so you have to look things up on a slightly different curve. And I talked about the person who invented the curve, the person who did the mathematics of the curve. He worked for the Guinness Brewing Company, and try to help a person remember what this is about. So for one mean or two means, if you don't know the standard deviation of the underlying population, and that's very typical, then you have to look things up on a slightly different curve. Okay, and we learned that when you do look things up on a slightly different curve, you have to do something again a little bit. We don't go into the theory of it, so it might strike a person as a little bit peculiar. It turns out the theories are all very sensible, but you have to work with what you got. So we had to know the sample size, and then we subtracted 1 from it. Remember that? That was called the degrees of freedom. We took the sample size and subtract 1 from it. Well, we're going to do the same thing here, except that we will take the two sample sizes. If, for example, this is fourth grade boys and fourth grade girls, taking a math test, we will take the number of fourth grade boys minus 1, the number of fourth grade girls minus 1, so we'll have two different numbers, and we will type in the smaller of those two. Okay, so when we come to popping up stat key, I will look at the number of things in the first sample -1 and the number of things in the second sample -1, and I'll find the smaller of those two, and that'll be the degrees of freedom that I pop in. Every one of these has some small twist. It's not an especially important, but a person just writes it all on that one page in the book. Don't forget to use the T-curve, exclamation point, and goes with that. Okay, and as always, there's some fine points here that it just happens that in our present context I'm not gonna go into at length. So I only want to do two questions. I want to do a confidence interval example, and I want to do a hypothesis test example, because not because this is any fool can see no such thing, but instead because this is exactly the same thing we've seen before. There's a slightly different formula, so I'm going to work through it, but it's exactly the same thing we've seen before. I'm trying to emphasize the unity instead of the differences. Okay, so for the confidence interval question, I'm going to do number 194, just to pop it up. Let me see if I can get the darn thing to go. What's going on? Video capture. There we go. Question 194, and I know it's hard to read, but you can bring it up on your own book. So it says, does red increase men's attraction to women? I mean, whatever kind of stuff. It says examines the impact of the color red on how attractive men perceive women to be. In the study, men were randomly divided into two groups, asked to rate the attractiveness of women on a scale from 1 to 9. Men in one group were shown pictures of women on a white background, while the men in the other group were shown the same pictures of women on a red background, and all this kind of stuff. They want a 90% confidence interval for the differences in mean attractiveness. And again, can't overemphasize this, trying to keep saying it over and over again, tell myself before I sit down to do these, don't forget to say that it says differences in mean attraction rating. That does not mean x1 hat minus x2 hat. That's not the difference they're talking about. They're talking about mu1 minus mu2. If we tested every man in the world with a white background and every man in the world with a red background, we'd know mu1 and we'd know mu2, and then we'd take one minus the other. Well, of course, we can never test every man in the world. We're going to work with the sample that we have. That's the best we can do, but that's what we want. So the confidence interval is going to tell us where that number lies. And they want a 90% confidence interval, and they gave me some data here. And I know it's hard to read, so I'm going to move it off to the side and do the example on a piece of paper. Okay, so I only showed you just for an instant the formula, so I'm going to copy the formula onto the paper here. Let's see. So we're looking at it's the usual confidence interval thing. Oh, this is number 194, 6.194. It's the usual confidence interval thing. I'm looking at x1 bar minus x2 bar. So that's going to be the average attractiveness rating. I don't know what kind of creeps it's talking about. Average attractiveness rating for white background, average attractiveness rating for red background. Plus and minus. I got to write down the T number there, and we'll look that up on the T curve in just a second. You got to give me a chance. And then this formula that we don't memorize the formulas, we don't worry anything. They're all on that one page, open book, open notes. Just use that page. It so happens that the formula is S1 squared over N1, S2 squared over N2, and that's it. So we are working with the standard deviation of the sample, not the standard deviation of the population. That's why we're using the T-curve. So this is just like section 6.2. Put a little note in the book next to that line and say, don't forget, use the T-curve in that context. Okay, so since the T-curve is on my mind, let me bring up the T-curve. Let's see here. Too many buttons to punch. Let's see. I want window capture. There we go. Window capture. And I hit the wrong darn buttons. Okay, so I want a T-curve. So here I go, T-curve. And it so happens when you read the book that the two samples are, there are 15 for the red case and 12 for the white case. So I don't look at 15 and 12. Instead, I look at 14 and 11. I know the minus 1 is kind of annoying, but there's a good theoretical reason for it. Anyway, you just do it. So write a note on that page. Don't forget to. So you look at not 15 but 14 and not 12 but 11. Take the smaller of those two. So you look at degrees of freedom equals 11. Because I took the 15 minus 1 and the 12 minus 1, and the smaller of those two is 11. So here I go, type in an 11. And I'm asking StatKey for a 90% confidence interval. It comes up with 95, so I got to tell it 90. 0.90, and there's the number I want, 1.796. 1.796. Okay, let's get rid of that and write on my piece of paper 1.796. 1.796. Oh, my mouse is in the way. Square root of. I'm just going to drop in the numbers, plus and minus, and x1 bar and x2 bar. So 7.2 and 6.1. 7.2 minus 6.1. 1.796. S1 is, they told me, 0.6. 0.6. N1 was 15. Oh, I forgot to write the square. And then S2 was 0.4. N2 was 12. And I'm done. I mean, I'm going to punch out all the numbers and everything. That don't get me wrong. But I'm basically done. I recognize that it's a T problem because there are two means. That's the first part of being done. The second part of being done is I knew how to use the T, the T part of StatKey. I had to look up the right degrees of freedom, and so you had to look at the two numbers of the two sample sizes and subtract one. Which of the two is smaller? The answer is 11. And then the third thing is to work out the numbers. I'll work them out. Anybody can flub up the numbers, but it's not really hard in some sense. And then the fourth thing is to remember what the confidence interval is about, and I already reviewed that. The confidence interval is about not x1 bar minus x2 bar. It is instead about mu1 minus mu2. If we didn't take a sample, if we took a census, what would we get? Okay, so let's see how I do with the calculator. That's not my biggest skill. Okay, so I got to take 0.6 squared divided by 15. And I've already said before, I like to do this in two stages. Some people are whiz with calculator, but I'm not. 0.024. And anyway, if you're careful, then you can go back and check it later. 0.4 squared divided by 12. 0.013. Take the square root, multiply by 1.796. And add it to, let's see, what's 7.2 minus 6.1? Isn't it 1.1? 0.024 plus 0.013 equals, take the square root, equals, multiply by 1.796 times 1.796, and that's about 0.35. So 1.1 plus and minus 0.35. I like to do the ends. I know you know that I like to do the ends. So that's 1.45 down to, what's 1.1 minus 0.35? 1.1 minus 0.35, 0.75. Okay, and again, the key thing is what's the idea, and the idea here is that this is not where x1 bar minus x2 bar lives. Instead, this is, we think that we are 90% sure that mu1 minus mu2. Were we to take a census, what a foolish thing to take a census on, but were we to take a census, we think that mu1 minus mu2 is in there. Okay, so confidence intervals are about the census numbers, not about the sample numbers. So the formula, person picks the right formula because when you read the question, there are two means. Because it's means, you have to do the t-curve. Drop the numbers in, a bunch of button punching, interpret the answer. Okay, so again, we did the hard work in Chapter 3 to try to figure out what confidence intervals are about, and I think it's paying off, frankly. Okay, then I only want to do one other. So I want to do hypothesis test, of course, and I was going to do number 214. So let me bring it over. Get a good picture of my desk. Question 214. It's kind of a long one, so I'm going to cut out some of the talk. It says, are babies able to generalize from sample the population? So it says 8-month-old infants watch somebody draw a sample of 5 balls. Each sample consisted of 4 balls of one color and 1 ball of the other color. After observing the sample, the side of the box was lifted so the infants could see the balls inside. Some boxes had the expected population with balls in the same colored proportion as the sample, while other boxes had an unexpected population with balls in the opposite color proportion from the sample. Babies looked at the unexpected population an average of 9.9 seconds with a certain standard deviation, and the expected population for an average of 7.5 seconds with a certain standard deviation. Sample size in each group was 20. Assume the data in each group is reasonably normally distributed. Convincing evidence that babies look longer at the unexpected population. Okay, so we have 2 averages, an average for unexpected and an average for expected. We have x bar for unexpected, x bar for expected, not mu. What we'd like to know is mu. So we'd like to know, is there really a difference between the 2 mu's? Or is this just a sample thing because you only looked at 20 babies, for crying out loud? It's not. Wasn't the world's most sophisticated experiment. Okay, so let's have a look, see how I do. So this is number 214. Just to write down all the numbers, I know they were hard to read. So I'm looking at x1 bar is 9.9. x1 bar is 9.9. S1 is 4.5. And N1 is 20. And then x2 bar is 7.5. S2 is 4.2. And N2 is 20. Okay? All right, so now it's time to write the hypotheses down. H0, HA. Again, trying to emphasize the sort of big picture, I'm not going to be arguing about x1 bar and x2 bar. There's nothing to argue about. We had some numbers, we divided them out, that's just what they are. What we're arguing about is mu1 and mu2. And the question says at the bottom, is there convincing evidence that babies look longer at the unexpected population? So that's the ones. So we're arguing about mu1 and mu2. Mu1 and mu2. Always, H0 is always equal, always. So that just leaves me deciding this one. And again, the question says, is there convincing evidence that babies look longer at the unexpected population? So they want me to write that. Is this right, or is this right? And again, I always like to do mu1 minus mu2 equals 0, and mu1 minus mu2 greater than 0. Okay? So hypothesis test, I hope we spent a long time on hypotheses. Hope continues to make sense. I hope so. And now we're ready to run the test. Test always starts the same way. The magic 2 words. Assume H0. Okay. Then we get a distribution of samples. The distribution of x1 bar minus x2 bars is the sampling distribution would look like this. It's got a center of 0 because that's what H0 thinks, and we assumed H0. H0 thinks the center is 0, and it's got a spreadedness. And who can remember the darn formulas? But anyway, we don't have to remember them. They're all written down. S1 squared over N1, S2 squared over N2. Why don't I punch that out while I'm working on it? This is S1 is 4.5 squared over 20 and 4.2 squared over 20. Let's see what my calculator thinks of that. 4.5 squared divided by 20. 1.0125. Oh, I didn't quite get it on the screen. There we go. 1.0125. And 4.2 squared over 20. .882. Add them together, take the square root, see what happens. 0.882 plus 1.0125, 1.0125 equals, take the square root, equals, and I got 1.38. Okay? And again, just anybody can punch a wrong button, but in a context where numbers are like 9.9 and 7.5, 1.3 seems like, I mean, if we got 200 here, I'd be wondering if I punched the wrong button. But in a context like that, having a spreadedness of 1 1/3 seems perfectly possible. Okay, so back to the usual hypothesis test stuff. We assumed H0, the distribution looks like this with this spreadedness, and all we got to do is figure out, is our number 9.9 minus 7.5, is our number crazy way off, or is it perfectly everyday? That is to say, what's the p-value? So the p-value of x1 bar minus x2 bar, what was that, 9.9 minus 7.5, 2.4 is. So I'll draw 2.4 and shade the area, and then I'll go look it up. Okay. So again, hypothesis test always works the same way. You assume H0, that gives you a sampling distribution, and you figure out where is your number on that sampling distribution. Is it crazy way off, or is it perfectly everyday? If it's perfectly everyday, then the H0 people will say that's a perfectly everyday sample. You haven't changed my mind. If it's crazy way off, the H0 people will say, really, I guess what I'm trying to claim is just not believable then. Okay, I'll change my mind. All right, so of course I have to bring up the stat key. And just to go back here to the original, like sometimes so many things here, I like to make sure a person can find what we're looking for. So this is a means question, so we're on the t curve. The first sample is 20, the second sample is 20, so I'm looking for the smaller of 19 and 19. Well, that's not 19. And I got to figure out here, where is 2.4 on my curve? Well, of course, I don't look up 2.4. That's not right. I have to look up instead 2.4 divided by. So I go back to the paper. To go back to the paper, I have to convert this into number of standard error units. I have to convert it to what we would have called a z-score, except that we're on a t-curve, so we call it a t-score. So that's not hard. We take 2.4, how far away is it from the center? The center is 0, divided by 1.38, and that's the number I'm going to look up on the curve. Okay, I have a couple people asking me questions about this particular step. So that's the number that we're going to look up on the curve. Anyway, here we go. 2.4 divided by 1.38. 2.4 divided by 1.38. And it says 1.74. So that's about 1.74. You would call that, instead of a z-score, you call that a t-score, but it doesn't matter. The point is that 1.74 is the number I'm putting into stat key, because the curve has got to see the standard value. All right, so here we go. What is it? 1.74, 1.74, 1.74, there we go. 1.74, 1.74, and I've got, just a hair under 5%. The tiniest bit under 5%, 0.049. So coming back, the p-value is 0.049. That's under 5%, but just barely. I mean, come on, this is a practical class. 4.9 and 5% is so close that a person would say, you know, I'm not sure this is really convincing data. Anyway, it's borderline data. But it so happens that when you read the question a little further, I didn't read all the way to the end. They say use alpha equals 10. Use alpha equals 10% instead of 5%. So with alpha equals 10, we find that 4.9% easily meets the alpha equals 10 criteria. That is to say, to the H0 people agreed in advance that any p-value less than 10% will make them change their mind. We came up with a p-value of 4.9%, so they do change their mind. We reject H0. Okay? So again, trying to emphasize the unity of what's happening here. How would a person know if you read a question, you know, let's say, you know, a year from now you're in sociology class and you're reading a question, how would you know what formula to apply? Well, there are two different means. That's how you know. So we're in the two mean section. The hypothesis test, we spent an awful long time talking about the different hypotheses. Of course, a person can forget. It seems like a long time ago, to be perfectly honest. But nonetheless, we spent an awful long time on it. Don't forget, the two key errors that I always see is these are not x1 bar and x2 bar. These are mu1 and mu2. These are population numbers because population numbers are what we care about. We're arguing about the population. We know the sample. We took the sample, did the division. It's all fine. We want to know the population. Population numbers, and then that's always an equal. And this one here, the question has to tell you that. I mean, you can't guess. So somehow, by reading the question, you have to deduce whether that's supposed to be greater than, or less than, or unequal. Then the hypothesis test always works the same way. You assume H0. That gives you a distribution of samples. The formula, it's a formula. You know, we're not doing the derivation. It's just a formula. You punch in. Hopefully I did all the numbers right. Anybody can make a mistake, but it seemed like it was a reasonable answer. And then you see where is our sample. You don't put in the raw number. You put in instead the standardized number. So you take the raw number, the 2.4, minus the center and divide by the spreadedness. So again, I got a couple questions about that in the last couple days. So very good. So either Z or T, depending on whether you're doing proportions. Proportions has Z, or means. Mean has T. And then stat key has to give you the answer. You're not just guessing. Stat key gives you the answer. You compare it to alpha. If no alpha is given, then alpha equals 0.5 is what you're supposed to mean. But anyway, you compare it to alpha and either reject H0. If the p-value is less than alpha, you reject. If the p-value is greater than alpha, you fail to reject. Okay. Okay. Again, so they all go trying to emphasize the unity. They all go something like the same way. Okay. Very good. So I hope everybody is well, and you know, we're getting down near the end, so a person can kind of take a breath and say, you know, starting to see the end. It's always nice to see the end. Okay. Bye bye.